So let's look into applying the Nernst equation to a galvanic cell, one that we've been looking at already. One thing I'll just point out, if we want to find the overall voltage for a galvanic cell, right? If we put a potentiometer on it, what voltage are we going to measure? Is it going to be positive? Is it going to be negative? We take the total potential, E total, or often just written as E, will be the difference between the positive electrode, so whatever is on the positive terminal of your potentiometer, minus the voltage on the negative electrode, whatever's on the negative side of your potentiometer. Now, I'm not saying this specifically as cathodes and anodes, because sometimes you can hook up your potentiometer backwards of which way the electrons would like to flow. So you might calculate a negative voltage. That means the electrons want to go opposite of how, right? So the electrons want to go towards the negative side that you have instead of the positive side, meaning that you should have flipped around your potentiometer. But sometimes it just depends. Maybe your positive terminal is always a standard electrode, and your negative electrode is changing. Anyway, there are different reasons why you might measure a negative potential instead of a positive one. So one thing I'll just note here is, for these both reactions, even though one of them is going to be an oxidation, both reactions are written as reductions. And the fact that we have this negative sign, that accounts for the fact that one of them is a reduction, or is an oxidation instead of a reduction. We'll say the oxidation at the negative electrode, right? Because that's where the electrons are being produced. So this negative sign right here takes into account the fact. So you don't need to reverse signs or anything. That's built into the way we do the calculation here. And so how we go about doing this is there are multiple ways to do this. You can combine the positive and negative electrodes into sort of one big calculation. You can do them separately. We'll do them separately. But let's find the voltage of a silver cadmium cell like we have, where we have these two, right? So we're going to have these half reactions are what's going to matter. 2 silver plus 2 electrons going to 2 Ag solid. And this has a standard reduction potential of positive 0.799 volts. And one thing I'll mention is if you look this up in your textbook, it won't have the 2 in front of it. I'm adding the 2 to balance the reaction equation. But adding 2 does not change the potential. It doesn't change the amount of force. Force isn't really the right word, but amount of potential energy pushing on our reaction. So standard reduction potentials don't need to be multiplied or divided if you multiply or divide the reaction that goes with them. And then cadmium 2 plus. Again, we're writing these both as reductions, even though we know that the cadmium is going to be an oxidation, going to cadmium solid. And if we look up this standard reduction potential, it is negative 0.402 volts. Now, if these were both at 1 molar concentrations of our silver plus and cadmium 2 plus, then we could just call this one our positive, this one our negative, subtract these, and be done. But we can't do that. So we need to go through and calculate, using the Nernst equation, what the potential is here. Okay, so let's do that. All right, so we'll do E plus first. Right, so our positive electrode is our silver. All right, so E plus is going to be equal to E plus naught, our standard reduction potential, minus 0.05916 volts over N times log base 10 of, and now we can look at our specific, again, we're going to ignore activity coefficients and do this just in terms of concentrations. So we're going to have products of reactants. Our product is a solid, so it doesn't show up. We're going to have 1 over the concentration of silver squared. And one thing to look out for here, and again, I can also substitute here this n, this is equal to 2. So this is one reason I wrote the balanced equation, to make sure I have the correct numbers here. We do need those to match up. Okay, so, oh, I forgot to specify. For this particular reaction, we need to know the concentrations. I have that in my notes here, but forgot to write it up here. So we're doing this for a solution where we have 0.5 molar silver and our concentration of cadmium nitrate is 0.01 molar. Okay, so if we want to find the potential of the positive electrode, all right, so we take our standard potential, 0.799 volts, minus 0.05916 volts divided by 2 times log base 10 of 1 over 0.50 squared. All right, so I'm going to pull up my calculator. We can go ahead and plug this in. Once it loads. It's sure taking its time today. Okay, there we go. And hopefully this isn't messing up my video too much. I hear my computer working a little bit. All right, so we have 0.799. Oh, number lock. 0.799 minus 0.05916 divided by 2 times log base 10 of 1 over 0.5 squared. All right, and that gives us a value of 0.781 volts. So we can see this is a little bit smaller than the standard reduction potential because we have not 1 molar silver, but we have 0.5 molar silver. All right, we can repeat this calculation for E minus. We're going to have E minus naught minus 0.05916 volts divided by N, and here is still 2 because there's 2 electrons. If we go back up to this reaction up here, there's still 2 electrons involved, times log base 10. And again, we write these as reductions. So our product is the solid, our reactant is the ion, so it's going to be 1 over. But this time we won't have the squared because there's only one, the stoichiometric coefficient is 1. Okay, so then we can plug in negative 0.402 volts minus 0.05916 volts over 2 log base 10 of 1 over 0.010 molar. Okay, and then we can find this standard reduction, this potential, negative, not minus, but negative 0.402 minus 0.05916 divided by 2 times log base 10 of 1 over 0.01. Okay, and that gives us a value of negative 0.461 volts. I always make it a point to make sure I remember the positives and negatives here. Okay, so what is our overall potential? So our E total for this galvanic cell is E plus minus E minus, which is positive 0.781 volts minus negative 0.461 volts. We go back to our calculator, 0.781, and it'll be plus 0.461, gives us a voltage of 1.242. 1.242 volts. All right, and so that's an example of how we can use the Nernst equation to find the potential for a reaction that is not under standard conditions.